Well, welcome back after the weekend, everybody, and a cold weekend to that. Good steady weather, so hopefully you did nothing but study, and which I guess that's why you guys decided to do the test today. So I'll pass it out.
Okay.
No, just kidding. No. So, but we'll do some more examples. I don't know if you recall. But the last time we were together, we were doing an example of a weight going up and down, and we had done part A, but not part B. So let's start that one again. We'll review part A real quickly, and then we can finish up B. And then we'll just go through the rest of my list. I've got a lot here. I don't think there's enough time to do all of them. And then the point is not to necessarily do all of them, but to just do one more, and each one has one more little twist or something a little different. And like all the example problems we do, we know that we can't do all the different combinations. That's never the point. The point is to do enough combinations so you get that feel of what physics is about, how to apply some very few but powerful fundamental concepts to explain the universal phenomena. And that's what we're after. And so hopefully by doing all these examples that I do for you and you read in the book and then your homework that you practice, you're prepared to come into the test and realize there's probably 100,000 different types of problems, and the one you're going to see on the test is still going to be different than the one that was on the homework and the ones that were in class, but the principal concept is the same, and so you start from there and you work out the details. So that was the intent, and that's the point. And this one in particular, and was it number 7 or 12? It was one of those two early on my list here. Let me jump to chapter 8. Looks like it was 12. No, that's the next one we're going to do. So we'll do 12 next, but it's number 7 here. And number 7 is this weight going up and down. And also, if you recall, part of the reason I was doing it was setting the stage, that in the pendulum one, or we had a swing, but in class we'll have a pendulum, is because that is today's lab. So I think I mentioned that, want to emphasize it again, that you have two parts here in the lab, a part 1 and a part 2. Both of them are going to be calculating the energy, and as you know from the equipment, you'll mark the position of the weight in the pendulum. It goes back and forth. With the weights, they go up and down, but you measure them like 20 times a second. You know, what's the energy now, and you just see, and you know, fortunately you have a computer that can collect the data real quick, and then you'll just see that the energy, no matter where it is on the way down, is a constant. And like I said, you'll see that for the pendulum, and you'll see that for the weights. So back to this weight one here. If you recall, this was the picture. They had some weights and much bigger space than we will have in the lab, but the concept is the same. They'll take a pulley and they'll tie it to the ceiling. Now in our case, we won't actually tie it to the ceiling, but we will have it on our bench rods. And then we're going to hang a heavier weight, and I forget the numbers that we'll have in lab. We'll see it here in a little bit. But this one has the 5 kilograms up here, and then down here on the ground had the 3 kilograms, starting with the 5 kilograms 4 meters above the ground. And so the first part, A, says determine the speed of the 3 kilogram object just before the 5 kilogram object hits the ground. Okay? And so I'll start off by saying energy initial equals energy final. There you go. And so maybe I'll say it one more time. Do you want all the answers to chapter 7 and 8? And you want half the answers to the test after spring break? Well, there it is. That is half of it. You want the other half of the answers to the other half of the test? And all the answers to chapter 5 and 6, there it is. So there's 5 and 6, there's 7 and 8 here. Now, in our case, let's put the details in for this particular setup. And so we did this one, and what we did is we started writing it out. We said, well, there would be an initial kinetic energy, there would be an initial gravitational potential energy, there would be an initial spring kinetic energy, there would be other energies or other forces, perhaps. And so that was our general answer. Those were the 4 on one side of the equation. Then on the other side of the equation, we had 1/2 mv final squared. We had 1/2, mgy final. We had 1/2 kx final. And then we had any heat that was kind of created in the process, which I guess we wrote as force of friction times the distance traveled. And now that I think about it, I don't even know if we wrote out every term. We said, look, we're getting a little more sophisticated now. There's no point in writing every term every time because we don't often have all of these energies. In fact, this list is going to grow, just to give you a little warning. I don't think it's going to grow anymore this semester. But there are other forms of energy, and so as we get into next semester, we'll have electrical energy up here, we'll have solar energy up here. You know, we will add to this list, and the amount of energies grow bigger and bigger and bigger, and no point in writing them all out. For example, this one has nothing to do with a spring, so there was really no point in ever putting that one up there. There's no springs in the problem here. And then likewise, we should have crossed out this one and this one. There is no frictional forces. There is no external thing pushing on it. That's coming up real soon too. And really that's all we need is kinetic energies and gravitational potential energies. And the reason I like this problem and picked it as an example back on last Wednesday is when we say kinetic energy, this is the first one we had 2 different objects. So we got to make sure we include both objects here. So as we repeat what we did on Wednesday, we said, well, what is the initial kinetic energy? And we put a 0 and a 0, saying, okay, both of them start from rest. And then we said, what is its gravitational potential energy? And that's where you want to pause, because to define the gravitational potential energy, you need to choose where does y equal to 0. And so, again, last Wednesday, we chose this. We said, all right, let's take the bottom down here to be y equals to 0. Seemed like a good choice, and I agree, it's probably the best choice, because what that does is it allows one of the objects to have an initial gravitational potential energy of 0, because it starts down on the ground, those 3. The only one then that really has any energy is this 5 kilogram, so it becomes 5 times 9.8 times 4 meters up. So there is the first part of the one. And so like I said, all these others are 0, 0, 0, 0, 0, and as you gain more experience, it would just make sense to just write that. I mean, if you stand back and look at it, you're going to go, look, there is no other energies except for that one right there. Nothing's moving, no kinetic, no springs, no heat, but this one is up into the air, if you will. It's above the ground. This one has gravitational potential energy. So, like I said, as you gain more experience, don't worry about writing all of them. Just write that one. And now, to the other side of the equation is, okay, what happens? And so this is really where the physics comes into play, because it's so easy to miss what happens. So that physical picture, that intuition of watching the things move come into play, because we got to add up all the energies. And so again, kind of quickly, so we can move into B, we watch this in our minds anyways go something like this, with the idea that right before impact, both of them are moving. And both of them are moving at the same speed. And so we wrote down 1/2 3v squared plus a 1/2 5v squared. And so we had the 2 terms because of the 2 objects, both moving, and both moving with the same speed. So we didn't have like a v1 and a v2, although that's why I picked the next problem, but more when we get there, okay? But these are the same speed. And then going on down here, we would say at this point, this 5 has come down here and has now no potential energy, which probably don't need to put a 0 now that you're a little more experienced with it, and particularly since by the time you take the test, it'll be 2 weeks now, so you got a lot of time. Probably won't need to put a 0 there, but this one will be up in the air. And you have to realize how high it is. And again, you get that from the physical picture. So the same logic we used to say they were moving at the same speed is the same logic that says this one then is going to be 4 meters up. And so we know the height of that one. And so the mass is a 3, and then it's a 9.8, and then it is 4 meters up. And so as we left class on Wednesday, we just finished. Oh, good. For what? 4.43 meters per second then is what we came out with, right? Okay, so if that jogs your memory and gets you ready for the next set here, then let's go on to B. And again, I like B because it again illustrates how powerful this conservation of energy is as a principle, and how really it's very powerful, but the equations really aren't that hard to do. Notice there's no integrals to do, essentially because we've done them already. There's no vectors to do, again, essentially because we've done them already. And so it just turns into a lot of plug and chug, except you got to really pay attention to the physical picture of what's going on and what's meant in here. And so we saw that here in terms of same speed, same height. And then we'll see that here in this question. But if you see it, it really falls into an easy problem. It says here, find the maximum height to which the 3 kilogram object rises. And then that's all they say. What do you mean? What do they mean the maximum height? I mean, it went up 4. Isn't that its maximum height? Is it going to go higher? I mean, why would it go higher? And what would be happening when it goes higher? In other words, what happens next? What happens at A? Where this is down here, just ready to hit the ground. This is up here, and then what happens? Yeah, and most of you see it. Good. I mean, you see what happens to this gun. Yeah, it makes an impact into the ground. Something like that, you know, hits the ground. What happens to all the kinetic energy that this one has? Yeah, it goes to heat, right? It hits those molecules start going faster. And so we could say, okay, there's an impact heat here. It's still a heat. You might say it's a little different than this heat. This heat was created by the rubbing or the friction. Either way, it's a rubbing. Either way, it's a molecules moving faster here. But if I were to figure out how much kinetic energy that one had, which was this one right here, right? That then ends up going to heat in that next little step here. And so I can take the speed I got, I go back, and I could get heat. Now that's not the question here, but I did want you to see that that could have been the question. You know, what happens to that object? Well, its final speed is 0 and there's this much heat. But it doesn't. It goes on to ask about this one. So up here is this 3 kilogram. What happens next? And I think I've drawn my picture a little misleading compared to them. So maybe it will help if I extend this. They gave it more room. They gave it up like that. And so here's the pulley. But the idea they're trying to get you to see here is when this one makes impact with the ground, this one's going to keep going up for a ways because it does have some kinetic energy. But it's not being pulled up by that 5 anymore, and that's kind of the key. The rope, if you will, goes loose, and it still goes up, but only because it has a speed. How much speed? Well, that much speed. So now, if I come over here to B and I say, okay, my initial energy equals to my final energy, and I think about all the energies, and let's not write them all out, it I think does become a much easier problem than A because I don't have 2 objects involved anymore, and that's a key step there. That's the physics step. Don't worry about the second object. Does the second object take some energy with it? Yeah, so we are not going to say all the energy that we started in part A is the same as over here. But what I am going to say is that if I take the 1/2 times the 3 times the 4.43 meters per second squared, whole quantity squared, and the 3 kilograms over here, and say that is the kinetic energy that just the 3 kilogram block has when it's, you know, making the impact. I would also say that that 3 kilogram block has this much potential energy also, right? It's 4 meters above the ground. That is what I'm going to call then my initial energy, okay? And again, this is just that opportunity for me to emphasize again. Be careful on what you mean by your system. 1 object, 2 objects, 3 objects. Be careful what you mean by initial and final conditions. But if you're real careful with thinking about what you call initial and what do you call final, then And then it falls into place pretty easy. So they become easy problems once you get over that hump of the physics, and making sure you see that. And so B, mentally in my mind, is a little different than A. A was the total energy of both objects as they moved up and down. But that's not what I'm doing here in B. B is very different. B is only one object. And so it has this much and then this much. And so I've focused on a different object. I've also focused on a different initial conditions. In other words, B, the final condition of this one block, is the initial one for part 2. And then once I know that, then I can go to the other side of the equation and say, okay, I'm trying to figure out how high it would go. And you don't necessarily have to put a 0 when you're doing your homework or your test. But wouldn't the kinetic energy be 0? I mean, that's the key to the problem, or another key to the problem in terms of doing the physics, of well defining what do you mean by initial and final. So my initial is right as the 5 kilogram block hits the ground. My final then is what happens to that 3 as it continues to go up and eventually comes to a stop. And so its kinetic energy up there is 0, and its gravitational potential energy then is the unknown, or that is, its height is unknown. And that's the unknown piece here. And so now, like I said, most of these, once you get your numbers in there, once you have a clear mental picture of the problem, the math is pretty easy because it's an algebraic type of problem here. And so putting the 1/2 times the 3 times the 4.43 squared, adding it to the 3 times the 9.8 times the 4, gives me my total energy of about 147. So all of that ends up as gravitational potential energy a moment later, and gives me about an even 5. So it continues on up for another meter. So that's why I said I need to draw it a little bit more like they have it, so I have room for it to go up a meter. You know, the way I had it, it was going to hit the pulley or hit the ceiling before it went up another meter. But assuming it has enough room to go on up another meter, that's what I think the author was after. Find the maximum height for which M2 rises. So that's the rest of the problem that we didn't get to. Shall we look at another one? Shall we go to 12? All right, let's look at 12. And again, start with that first step of getting a good physical picture of what's going on here. And that will really simplify the problem mentally, and it will become more than just a plug and chug type of problem. It'll want to be where you can read along, you can understand each step of the way and go, okay, what does each step say in terms of the energy? This one says, and it says review problem, and it kind of is. We had something similar to this back in chapter 5, but we are going to have to pull our information here from our pulley system that we did. 2 different objects moving. Watch. It says that the pulley system that is shown in the figure. Well, let me draw the figure for those of you who might not have the book in front of you here. Here's the ceiling. And it has the fixed pulley hooked on here, and a string or rope or cable of some kind that goes along, and then now here's that movable pulley again. And this your author calls block B, and next to block B at the same height and a better picture than mine, but same dimension, same mass and everything, is block A. So we start with 2 blocks, block A and block B. And so there's the figure. Now before I go and read the rest of the problem here, let's just kind of review this a little bit. What do you mean by movable pulley? What happens here? I mean, what would happen if I were to take block A and pull it down? Would anything happen to this block? Would it move? Would it go up? Would it go down? It's going to go up a little bit, right? And so as this one comes down, this one goes up. Or the other way around. What if I push block A up? What happens? then block B comes down. And so can you see that with the string? If I push this up, this string's got to go somewhere and it slags down a little bit. And what happens to this pulley? It moves down, right? So hence movable pulley. This one doesn't move, fixed pulley. This one does move, movable pulley, okay? And so these two are going to move in opposite directions. This one goes down, this one goes up. If this one goes up, that one goes down. Okay? Fair enough? Do they move the same distance? They don't, do they? Didn't we do this one before? Now, it wasn't a vertical movement. We had horizontal movement. But we did this back in Chapter 5 here. And so, again, for the sake of discussion, let's just say I pull this down a distance of RA. All right, you just told me that this would go up. Actually, I'll tell you what. Can I call this YA instead of RA? Only anticipating that the movement would be a vertical, so I'll use a Y instead of an R. But also fitting in with our equation for potential energies, we've been using Y's, not R's anyways there. So it'll be okay. I'm going to call this movement, say a down, a YA. What would happen to this block? Well, it's going to go up. Let me call it YB. And does YB equal YA? No. How are they related? And so there's got to be a connection between YA and YB. And I heard a half and I heard two twice. And so, good news is, yes, there's a 2-to-1 ratio. Yes, that's what we saw last time. Let's kind of go through it. I like to do it this way. I like to say, let's just say you actually did pull it down 1 meter. Okay? That means this string's got to come an extra meter. Where are you going to get that extra meter? Assuming the string doesn't stretch, where do you get the extra meter from? Well, that's the fact that, and I'll change colors, that this one is not as low. It goes up. And so it does something like this instead, right? And so from here down to say here, as well as say from here down to there, that's that extra short distance. So if this went down 1 meter, then we must have a half a meter here and a half a meter here. So this one must go up half of what this one went down. Fair enough? And you could put it either way, or even say it either way, but it does leave room for twice there. So twice the movement of B is A. So if B is the 1/2 we just talked about, you multiply it by 2, that gives you your 1 meter. Okay? And again, there's no way to figure this out from some equation you're going to plug into here. This is the physical part. This is, look at the physical picture, look at what's going on here. There's a movement of these blocks, and so what I need to know is the connection between those movements. Okay? And so there's kind of my first step. Understanding the problem, getting a good physical picture of the physics of the movement here that's going on here. And then once I have that done, then maybe I can, answer the question with a lot less trouble. And that's why I keep saying that. But I'll go on to read here. The first sentence again, it says, a system is shown in figure 12. It consists of a light, inextendable cord, and a frictionless pulley. The blocks have equal masses. It is initially held at rest, so the blocks are the same height above the ground. The blocks are then released. Find the speed of block A at the moment that the vertical separation of the two blocks is h. Okay, so there's the question. I'll read it again. Find the speed of block A at the moment the vertical separation is h. So maybe we should draw that next picture, that vertical separation of h. So here I have then this fixed pulley. And the blocks are going to separate. All right? So maybe I should start there. does A go down or does A go up? I mean, I know I wrote it here to get some kind of thought process that it's a 2-to-1 ratio. But I wasn't trying to say that A goes down. And so I think that's the next logical step here is decide, does A go up or down, or does it stay the same? I mean, they are the same weights, right?
Wait, what was the question?
So what is the speed of block A when they have a vertical separation of h? So I'll start with there. Do they separate? I mean, they're the same weight, so if I just left them alone, do they stay there? And if they don't, then which way does it go? Does block A go up or down? We already know that they go opposite.
A would go down because of your,
Yeah, A's going to go down. Why?
your advantage of your pulley system.
Okay, forget the fancy word, it has an advantage. So why do you say that? I mean, why do you say that A goes down? Yeah, okay, back to half the tension or twice the force. I mean, if I look at block A, I see block A being pulled down with mg. I see it being lifted up with T. What do I see for block B in my free body diagram? Yeah, I see it pulled down with an mg, but I see block B being lifted up with twice as much. Okay. And so obviously block B has more of an upward force. So if anyone's going to go up, it's going to be B. And they can't both go up, and they both can't go down. So from that alone, I would say, and that was your mechanical advantage statement. That was, hey, it has the advantage of the pulley wrapped around there. So it's got a 2-to-1 ratio here. And so clearly then, I would pick B. In fact, I'd go one step further. I would say that this gives me some information here. If this block A goes down, this is going to tell me that mg is greater than T, isn't it? But if block B goes up, that's going to tell me that 2T is greater than mg, or T is greater than 1/2 mg. So putting these two together, I'm going to say T is greater than 1/2 an mg, but less than 1 mg. And that would be perfect for this system, right? Tension's got to be somewhere more than 1/2 and less than 1. Because that less than 1 allows block A to fall down. But that greater than 1/2 allows the 2T to be more than the weight of block B and to lift it up, okay? And so there's your review part of this one. This is chapter 5. This is, adding our forces, our free body diagram. We haven't done anything with energy yet. We're still kind of just studying the problem, trying to get an understanding, a good physical picture of what goes on with this problem here. All right, so now, as I said, I will draw it over here after it has moved, and now I know which way it has moved. I know block A goes down, I know block B goes up, and I know that block A goes down twice as far as B goes up. And that's a lot of information. That's some very useful information. Let me just make a dotted line across there. And so here's my dotted line. So here's where they started. And so now I have block A here going down as we just reasoned out. And then block B would go up, but block B would not go up as much. And so I guess I have something like that, where then if I make a mark here, that separation is A. And this one is moving down with a velocity of VA, and this one is moving up with a velocity of VB. Okay. And so again, just kind of pausing on that first step. Got a good physical picture of what's going on here. Even though they're the same weights, because of the mechanical advantage, because of it wrapping around the movable pulley, there is going to be a drop of A and a rise of B. And this is the question: what is the velocity of A when we have a separation of H? And maybe I should do one more thing then. Let's look at the velocities. Is the velocity of A the same as velocity of B? It's not, is it? How are they related? Yeah, good. In the same way we saw that back in chapter 5, is once we know this, we can take the derivative of each side. And so we can say, take the derivative with respect to time of this. And over here, we would have what's the velocity of A with respect to time? How does it compare to the velocity then of B? And so we get velocity of A equals twice the velocity of B. So the fact that their movements are 2 to 1 also implies that their velocities are 2 to 1 and their accelerations would be 2 to 1. Although we don't need to know that. That's kind of the beauty of this particular approach using the energies, whereas in chapter 5 that's what we wanted. We wanted to know the relationship of the acceleration, so we took the derivative yet again. But we don't need that. Now, knowing distances and velocity, those are the two things when it comes into the energy. And so now I think we're ready to actually then write out the equation and solve it, now that we got the good physical picture here of what's going on and we've done our free body diagram here. So I will then say, all right, initial energy is equal to any final energy. So initial energy, we need to start adding things together. There is 2 objects here, so maybe I'll put 2 zeros and say that's the kinetic energy, because they made it very clear. These objects start from rest. Okay, so kinetic energy of A, kinetic energy of B, a 0 and a 0. But let's look at the potential energies. Gravitational potential energy. What's the first thing you need to do when you look at the gravitational potential energy? Its height, okay. But before you can look at its height, you need to define. Yeah, where are you going to put your origin? Where are you going to put y equals to 0? So help me out here. Where are you going to put y equal to 0? Remembering there is no one spot that it has to be. Every spot would work. Some may be better than others. Make the math a little bit easier. But it's your choice.
Maybe where the A is at the lowest point.
I heard one person saying, hey, lowest point here? You like that one? Starting at 0? Finishing at 0? All right, and I don't care either. Either one will work out. I do see this one is nice. I don't have any negative numbers, but I'm beginning to wonder mathematically if this wouldn't be easier. But I'll tell you what. Who wants to do this one y equals 0? Raise your hand. Just a couple of you. Who wants to do the starting point y? All right, so most of you want that one, so I'll go with that one. Do I ask about that one? Anyone want that one? No, good. Okay, so we'll go there. All right, so by a majority choice here, let's call y equal to 0 right where they start. Okay? Now, mathematically, that's kind of nice, because what does that mean about their initial potential energies? They're 0 also. So mathematically, they're nice there. But conceptually, physically, that may throw you off. So be careful here, because all of a sudden you're starting the problem and you say you have no energy. That almost implies you can't do anything, right? Can't go anywhere. But that's not quite what it means, right? Remember, you define energy equal to 0 anywhere you want. So all that is saying is the total energy has to be 0. So when this one goes down, it now has negative energy, which is perfect because this one goes up and has positive energy. And the total energy is still 0, still unchanged. So hopefully the 0 won't throw you for a little curve. But that is the danger of calling this spot, I think, y equal to 0, because you're like, whoa, wait a minute. You're starting with absolutely no energy. But that's okay, because 0 is just a reference point. Could you have less than 0? Sure. And now you can have negative. And sure enough, that's what's going to happen here. So this one's going to go down and have negative, and this one's going to go up, or B is going to go up and be positive. And for that matter, these are going to be moving, which is also a positive energy here. So when we add them together, we should have 1 negative and 3 positives, and the total should come out to be 0. Okay? And then we have our advantage of our math. One side of the equation equals to 0 is usually nice to have. All right, so I'll add it up here. So let's look at this side of the equation. When they get over to here, I will have 1/2 m times the velocity of a squared and 1/2 m times the velocity of B squared. So there would be my kinetic energy of each of them. And then I would have the potential energy, which I guess I would write it as mgya plus mgyb. And again, unless you look closely at this and realize positive number, negative number, A went down. And then positive number. So these three positives must add up to be equal to that one negative. Oh, and do I need an A? They're the same masses, right? Okay, so I don't need to put a M sub A or an M sub B because they're the same masses. Which actually I just realized then is really extra nice here because now I got that 0 on that side of the equation. They all have an M. They all cancel off here. And now I can start putting this some substitutions together. I will leave the first one alone because that is the question. What is the velocity of A? So I don't want to get rid of V sub A. That is the question. What's the velocity of A? But why don't I get rid of the velocity of B? I can do that because the velocity of B over here would tell me it's half the velocity of A. So I can write this as velocity of A divided by 2 squared. So there's my first substitution. And I've gotten rid of the velocity at B and only have it in the velocity of A. Okay? And then I think I have a little bit more work to do because they want this to be in terms of the height h, the separation. And neither of these are the separation. I mean, how do I get that connection? Right, okay, so I know that if this is at a height of B and this one is now at a height of A, when you subtract the two, don't you get H? I mean, that wasn't the whole point. One is higher than the other by a difference of H. Okay? And then for that matter, we could come over to here and say we got this relationship, although this is the part I think where we need to be careful. We might pay a price by choosing our y equal to 0 here. It was nice to start with, but if you look closely, doesn't this imply that they have the same sign? See, what we really said back here is that one went up and one went down. And so be careful there. But realizing that, then we can begin to substitute into here. For example, in place of this y, and I have to be careful. Is that an absolute value? Maybe I should do them all in absolute values. What if I did yb plus ya? How about that? Is h. Is that easier to see? Instead of with a negative sign? So you're saying one went down, ay, and not worrying about negative. I kind of like that. And then one went up. As long as I'm going to do this. Bottom line, I just want to be consistent with my math. It's again why I've been saying, I haven't said it for a while, so maybe I should say it, make sure you read the math while you're doing the math. Okay, what is it that you have? Applied math can be a lot different than just a mechanical math or a method math. And you're probably discovering that. Now, even though you're doing calculus, sometimes you're probably like, hey, this calculus in my physics class seems to be different than the calculus I just did for my math class. And hopefully you see it's not that it's different, it's that the integrals are the same, the derivatives are the same, but how do I know I was supposed to integrate? How do I know I'm supposed to differentiate? Well, I'm thinking the absolute value might be a better way to go. And then that would make that absolute value, but that didn't change. I didn't even address it then because they were the squares. So I was like, well, I'm not even going to worry about those. But I knew it was coming up here, and that could make this problem kind of tricky. It's a big reason I think your author lists it. He still lists it as a medium problem, but he puts it as a high medium problem thing. And I think this is why. He says, this can be difficult right here, realizing one goes up and one goes down. And it's easy to think about them in absolute values, and then you do an equation that doesn't think of them in absolute values, and now you have them mixed, and you're going to do your math wrong. So make sure those are there. So another big reason why I like this problem and picked it. So realizing that, then I can come over here and make some substitutions here and say, okay, the absolute value of b plus twice the absolute value of b is h, or put another way, 3 absolute values of b is h, or the absolute value of b is 1/3 h, which means then the absolute value of a is 2/3 h, right? And so you're really saying it went up 1/3 h, and this one went down 2/3 h. That makes sense, right? It should have a 2-to-1 ratio and should be separated by h, right? And that's what we have here.
Wait, why a 2/3 h?
Well, come back here. Here's the 1/3 h. Good with that one. And then a is 2 times of b. So I got b at 1/3 multiplied by 2, and it's 2/3. And then again, just to check to see if my logic was sound here, or my math was sound, I'll look at my answer I got. I got b going up 1/3 and a going down 2/3 h. Those should be 2-to-1, are they? Yes. And the total should be h, are they? Yes. So I got the correct ratio as well as the correct total. So did it right here. So now I can come over here and answer this question that I was trying to say is, let's put in the value of y. And in this case, y is a negative 2/3 h. And again, emphasize here, I'm not talking about the absolute value. Here I'm saying it is down. I chose y equal to 0. Okay? And then by your vote, you chose it to be here, and that's fine. And then it went down, so it must be negative. And remember, when this equation was derived, mgy, something very important was chosen for you. What was it? Direction. Up is positive, down is negative. So you can't choose that again. Can you choose where y equals to 0? Yes. But you can't choose direction. So once you've done all this stuff, either with absolute values or not, that's fine. But when you go to put it over here, you don't have that choice anymore. You've got to put in the value of down is negative. End of story. Because you use that equation.
Could we have done it without absolute value?
Oh yeah, we could have done it without it. We would have done this then. Without the absolute value, we would have said negative 2yb is ya. So there's still a 2-to-1 ratio in terms of their distance, but when one is positive, the other is negative. And then, like any number line, we would have said, take the height of one, subtract the height of the other, and the distance is h. So then, we would have had no issues of absolute value. Okay?
And you would substitute for a.
Oh yeah, so if you want me to continue to work this out, sure. I'll put yb here minus, and in place of ya, I'll put a negative 2yb equals h. A negative and a negative become a positive. This comes out to be 3yb equals h, or yb equals to 1/3 h. Well, knowing that and putting it to here, then ya equals negative 2/3 h. Yeah, so same thing. And so if that's easier for you, great. My concern though was right here. When I said the ratio was 2-to-1 with no negative sign, none of you guys said a thing. It's like, all right, I'll go with it. Let's see where this takes us. Because once you start doing that, for one of them you're calling down positive, and that's going to be a problem when you hit here. And so you got to realize that somewhere along the way, Otherwise, you'll run into troubles. So again, it's a good problem that illustrates. It's more than just plugging and chugging here. It's, you know, and like I said, you know, if you do plug and chug, I know you will get close. And I will see the logic, and I'll go, oh man, they're just messing up their signs and direction. Oh, I got to give them a lot of partial credit for this, but how much? Blah, 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 blah. And then you'll get an okay score. And you'll get an okay grade. And, you know, all right, so you'll get the idea there. But hopefully, you'll do more than just okay. You'll see those little subtleties, and not just a blind plug and chug, but what's going on behind the scenes. All right, so moving on. Now that we've answered that, this one then is a 1/3 h. And now I'm ready to really do the math to solve this. What is the velocity of A? So, a half and, so that's really a half and an plus an eighth, isn't it? So, what does that come out to be? 5 plus 1, 5/8? All right, so this is 5/8 VA squared. And this is a 1/3 with a negative 2/3, which is a negative 1/3 h. And that still equals to 0. So moving to the other side, I've got GH from here over 3 and a 5/8 VA squared. Well, I was hoping some of these numbers would cancel off. Doesn't look like it. Looks like I got an 8 over here and a 15 down there, a G, an H, a square root, and that's the velocity of A. So, got a lot of math to do. Hopefully I didn't do it too quickly. I know I did a lot of steps there. And mostly that's for the interest of time. I don't encourage you to do that many steps on the test. It's just too easy to make a mistake. And maybe I shouldn't then, because I'm a bad example. But the idea is, I think you know how to do the algebra. That's not what I'm after here, you do the algebra. I'm after this part. Set it up, go through the math, and then do the math real quickly so you can see the answer there. And that way we can go to another problem, which then says, okay, what is, you know, the speed of something else?
Wouldn't that also be negative?
Oh, fair enough. Yeah, fair enough. Yep, I'm back to that same thing. I'm taking the square root, and technically the square root is plus or minus. And then plus or minus, I need to come back to my physical picture and say, well, what is it? And then it is down, so technically I need to pick the negative one here. So I'll put the negative over there on that side. Yeah. So using that same plus or minus, or what I was doing mentally but didn't say it, was that. What's the absolute value of its movement? It is moving down. And I wanted to know its absolute value. What is the magnitude of it moving down? Okay. All right, well, let's try another one in here. Here is 14. And I think for the first time we've got one with some friction in it. And that's why I picked this one here. It's got some friction. And it starts off with no friction so that it can kind of lead you into, well, what happens then if you have some friction? And so I thought it would be a good problem for just that reason. It's this experience by doing these that kind of give you some insight to what happens with and without friction. And then that helps you with the next problem as you say, hey, I've never seen a problem like this, but oh, now I have. I've seen one with friction. This one says you have a 2 kilogram block and it is attached to a spring with a spring constant of 500 newtons per meter as shown in the figure. So the figure looks something like this. They've got a tabletop, they've got the block, they've got the spring anchored to the wall. Maybe I just better double check that. I'm pretty sure it says as shown in figure 9, actually 7.9. So going way back to chapter 7, figure 9. But I'm pretty sure, yeah, that's what they have there. And so they just got a block on a horizontal surface. They got a spring attached to it, mounted to the wall there. It says a 2 kilogram block is attached to a spring with a spring constant of 500 newtons per meter as shown in the figure. So let me go ahead and put my 2 kilograms there. Let me go ahead and put my K equals 500 newtons per meter there. And so there's my figure. A joule is a Newton meter, right? So yeah, that's not a joule. That is a spring constant. How much force you get for every meter you pull it. Yeah. It says the block is then pulled 5 centimeters to the right of equilibrium and released. All right, so changing colors a little bit here. To the right of equilibrium. All right, so maybe I'll put kind of a little dashed mark here and mentally tell myself, okay, that's equilibrium. Okay? So when I pull it to the right, 5 centimeters, I guess I'm over here somewhere. And I pull it to the right, 5 centimeters, and let's keep reading. What does it say here then? The block is pulled 5 centimeters to the right of equilibrium and released from rest. Okay, so you just let it go. You don't push it or anything. Find the speed of the block as it passes back to equilibrium if A, the horizontal surface is frictionless, and B, if there's a coefficient of kinetic friction of 0.35. So A is without friction and B is with friction. So what if there was no friction? We'll start there. What's going to happen here? Well, again, hopefully you see this as an energy problem, and maybe this would be a good time to say it explicitly if you haven't caught it, especially as you come up to the exam, because this chapter is all about energy. So there's probably no doubt in your mind that what do you need to solve it? Well, initial energy equals final energy, right? But before we got to this chapter, we had a lot of these equations. That forces equal mass times acceleration. And I must admit, especially for the beginning student, sometimes you got to ask yourself, what's the best way to solve this problem? Should I use forces and acceleration? Or should I use energy? Because can't both of those get you velocity? Right? And usually, not every case, I wish there was just one answer I could give you every time. It would make problem solving so easy, you know. It's like, do this, and you're done. But I suppose if it was that way, then everybody could do it, and, you know, this class would be packed, and, you know, we would have, you know, tons of, we wouldn't have problem solving issues in our country here. But we do, and there's very few people who really graduate with good problem solving skills because of that here. But here's the general answer for problems like this. Pay close attention to the information they give you. Is it given to you based on time? Or is it given to you based on distance? Because usually when it has time involved, the approach is through acceleration. Kind of make sense? Because time goes with acceleration. But when it has distances involved, it usually has to do with energy, because isn't that what we're working? Energy comes from distance. And the fact that they tell me they pull it 5 centimeters to the right and let it go is my clue. I'm going to try this with energy. Okay? They're telling me about distance. Okay? That's an important clue here. And so if you didn't catch that with the other ones, I should emphasize that now. Although, since we're in Chapter 8, you'll see every problem we do has to do with distance and has to do with energy. When they had to do with time, they were back over here usually. Okay? And we did our acceleration. And not to say you can't do it one way or the other. It's nice when both ways are possible. But usually one is harder than the other, and this way would be much harder than that one. In fact, this way you would have to do an integral which would lead you to that integral that's already done. So it would essentially come out to be the same problem, but you do a lot of beginning work only to get to here and then finish the problem. So start here. All right, so again, without any friction. So I'll start off and say, all right, how much initial kinetic energy do I have? Yeah, 0, right? I'll put a 0 there. It says released from rest. So don't overlook that. Oh, we've seen that so many times that I think that's well ingrained in you, so you're not going to miss that. You know, released from rest. Okay. What about gravitational potential energy? What about spring potential energy? And let's at least mention the gravitational potential energy. Doesn't it have to do with height? So where do you want to call y equal to 0? Yeah, and then if we call the horizontal y equal to 0, does it ever change? Now, perfect, right? So, be okay if I don't even just include it up here? So, like some of the problems that we didn't use the spring energy because there was no spring involved. This one does have a spring, but it doesn't have any uphill or downhill. So, we don't need to worry about height. So, I'm just going to just go right past gravitational potential energy. Not even relevant. And hopefully you'll see that and see why. But I'll go on to then the other potential energy, the spring. Do we have the spring here? Yeah. And so starting off then with the initial spring potential energy. How much do I have there?
What does the U stand for again?
U stands for potential energy. If you're going to go down the road of why the U, I'm not sure. I know some books use a U, some books use a V. And in fact, it reminds me of the dynamics class. A couple of my students who had, last year were in the dynamics class, and they saw me in lab, and they were asking, how do you do this problem? We've been really struggling with this one. And anyway, then I noticed they flipped open the book, and half the reason they were struggling is they were, what's this V? I don't remember seeing this in Physics 121. And I go, oh, okay. No, that's the potential energy. Just, mgy. Really? Yeah. Oh, then it's easy. Right. Good. All right. So, and the book also used a T for kinetic energy. It's also common. And then why, I'm not sure. My speculation would be had something to do with the Latin, but I don't know. Okay, so now to the spring. How do I calculate this? What is it? Is it 0?
Is it? Is it compressed? Or is it
Okay, so you guys got the idea, I think, here. Can I choose x equal to 0 anywhere I want? No, I need to go by the choice of Hooke's law for the x equal to 0. That was what I've been emphasizing for this last week. It's absolutely crucial. If you're going to be using the equation 1/2 kx initial squared, you need to realize it came from the force from a spring is minus kx. And that is based upon a zero force being, well, of course, the unstretched or uncompressed, what we call the natural length of the spring. So we need to read the problem carefully for what they mean by its natural length. And I don't know if it was as clear. So I'm going to read it again just to see what it says here. But it says a 2 kilogram is attached to a spring with a spring constant of 500 as shown in the figure. The block is then pulled 5 centimeters to the right. So maybe it's not as clear, but I think they really are implying this is the natural length of the spring. You start with the natural length of the spring, you put the weight there, and then you pull it. So this is not x equal to 0. This actually has some kind of distance. So I need to put in a 1/2 times a 500 times a 0.05 meters squared.
What do they give that in?
The 5 centimeters? Yeah, they say you pull at 5 centimeters. Okay?
Oh, okay.
Yeah. And so notice two things that I did here. Number one is I needed to know where does x equal to 0. It was a choice I didn't have anymore. It's a choice I gave into when I chose this. This is where I had my freedom of choice, which came from that. And so if I'm going to choose that, I have chosen that, and I'm stuck to live with it. Okay? All right. So I am now stuck on that choice. And then I pull it the 5 centimeters. So by my interpretation of it, this is the natural length. Then the second thing that you'll notice, it said 5 centimeters. I did not put centimeters here. Why not? Because this is in Newton meters. Energy comes out in joules. Buried inside of joules are kilograms and meters and seconds. And so I don't want any centimeters in here. So this brings us back to chapter 1 and paying attention to our units and our unit conversion there.
So it's asking how much force. What is the question for what are we solving for?
What we're solving for is when you let this go from rest and it gets back to equilibrium, Oh, then it's very clear. They did say equilibrium. Back to equilibrium, that's my x equal to 0. So the author did make it very clear. I want to know the speed when it's here. Okay? So again, I'm going to say initial and final. And maybe I should have been more clear also here is, remember, a key to this problem is, what do you define as initial? Okay? Do you define initial as starting here and then your hand pulls it? And if it is, then remember we have an energy from an external source. We haven't done any of those yet. Or do you call initial the point where you've already pulled it out here and you're ready to let it go? And that's what I'm calling initial. And I didn't make that quite as clear. But my initial point, my definition of initial, is when the block is right here and my hand lets go of it. So I don't have any energy from my hand, but I do have energy from the spring, which of course is where the spring got the energy. It would have been from my hand. So if you had called the starting point here and then your hand pulls it back, you would have made this a two-step process, realizing that your hand gave it this much energy. But I'm starting here. This is my initial spot. Starting from rest, with it pulled back 5 centimeters and letting go. My final position is when it returns back to this spot. Because that's the question. What is the speed when it returns back there? And so my final position then would be a 1/2 times the 2 kilograms times the speed squared. And that's it, right? That's all the energy you have there, because when as it moves on back, it doesn't have any spring potential energy anymore. And we already said it doesn't have gravitational potential energy. And at least in A, there's no heat. That's going to change as we come over here into B. But like I said, once you go through all of this physics part, the math's pretty easy. Plug and chug, one unknown, solve it for V, and you got the answer here. Okay? So here's the 1/2 times 500 times 0.05 squared divided by 1, square root of that, and velocity is, and as you pointed out last time, it's really a plus or a minus 0.79 meters per second. And I guess I then should decide what speed I have. Do I have the plus or do I have the minus? And again, since I pulled it to the right, and I called right positive, it's heading to the left. So I guess the best answer here, it has a negative speed. I can say the plus speed is what I would have got had I pulled it to the left or pushed it to the left and then let it go. And then I'd have a positive speed and I'd get the same energy whether I compressed it or stretched the spring. So it makes sense that I'd get the same speed, plus or minus. But I guess I'd want the minus one. Whereas then I can get into B, and B is what I wanted you to see. How would it change? Well, I think you will realize that this part would still be the same, wouldn't it? We start here with initial energy. And so that initial energy is the 1/2 times the 500 newtons per meter times the 0.05 meters squared. So that's still the same. But when you let it go and it gets back to equilibrium, it now has some speed, yes, but it won't be the same speed, more or less. A little less, why? Okay, because we're going to have to give some of our energy to our heat. And so because some of the energy goes to heat, we don't have all the energy going to kinetic, and so we'd expect a speed that is less. How do you calculate the heat energy?
Is it kinetic?
Yeah, it's a kinetic friction. So it's the force of kinetic friction times distance traveled. And so again, that's why I picked this problem, so we could take a moment and then calculate that one. We haven't done any of that calculation yet. And so let's look at those separately. I guess I'll start with R. How far did it travel? Yeah, that's still the 5 centimeters. That's, from where you let it go back to equilibrium. So that hopefully is the easier one. But what about the force of friction? What's that one? Yeah, it's the coefficient of kinetic friction times the normal. And they did give us that one. They said in B, the coefficient of kinetic friction between the block and the surface is 0.35. So we have the coefficient, but what else do we need? The normal. How do we get the normal? Okay, so we're back to free body diagrams. We're back to chapter 5. So certainly never forget any of the earlier stuff we've used. Okay, and so maybe I'll just draw the free body diagram out again here and say, look, there would be the force pulling it down, mg, there would be the normal force pulling it up, there would be the spring. So let me use a capital F with an S for the spring, not to be confused with static friction. But then that would be pulling it back here. And as I added up the forces in the y direction, there would be the normal force pulling up, gravity pulling it down. That has to equal the acceleration in the y direction. And the acceleration in the y direction is 0. And so the normal force is mg. Does the normal force always come out to be mg? Yeah, all right. We did a lot of that in chapter 5. Just wanted to remind you. It does not always, but it does in the easiest of cases. And this is one of those easiest of cases, at least easy in the vertical direction, not the horizontal. But there is my normal force. So knowing that, then I can do this 1/2 times a2 times a v squared. And then I get my 0.35 times my normal force of mg. And so there's my mg. And then there's my distance of 5 meters. So distance, normal force, and coefficient. And so this is where that extra energy goes. So again, grabbing my calculator, I'll do this side, 1/2 times 500 times 0.05 squared. Subtracting off this energy, 0.35 times 2 times 9.8 times 0.05 gives me a lot less energy to work with. Dividing by 1 and then taking the square root of that is a lot of math, I know. Don't try to do it too quickly. Hopefully I didn't make a mistake doing it too quickly, but there's the speed I got, and hopefully it's less than that one. Oh, plus or minus, are we going to say? And this should be a minus, so it's still going back? No? No?
Isn't the spring constant negative 500?
The spring constant's never a negative number. It's 500. Help me out here. Why are you saying negative?
Because that equals negative kx.
Okay, yeah, the force from a spring is negative, the spring constant, so in this case 500, times the distance you stretch it. But the constant doesn't have the negative in it. The negative is in front of the constant. So what the negative is telling me that if I pull it over here where x is positive, let's say I pull it a whole 1 meter, I'd be 1 times 500 times the negative. That's negative 500. That means the force is that way, negative 500. If I compressed the spring, then my position would be negative 1 meter. And I'd have negative 1 meter times 500 times a negative, that's a positive 500. So as I compress it in, it's this way. But the spring constant K has never been negative. We do have a negative in the equation, but K is not a negative number. And so we don't use a negative number here. Otherwise, well, and we'd be really in trouble mathematically then, because then we'd be trying to take in the square root of a negative number.
Where did 0.35 come from?
Oh, from the reading.
Okay.
That said the coefficient.
They gave it to us.
Yeah. So in part B, they say in part B it has friction and that coefficient is 0.35.
If it was a higher coefficient, how would you then check to see if there's any movement at all? If the friction is sort of over.
Oh, I'll even go you one better. They weren't really fair in this. They already assumed it would move, Because remember, if we calculated the free body diagram right here, okay, we would have the force from the spring, and as you're holding it, there would then be a static friction. The force from the spring would be the minus 500 newtons per meter times 0.05 meters. Okay? The force from the static friction would be that. And we really can't solve for that because they did not even tell us what the coefficient was. So your question is, what can I say? I mean, it's a good question and something that needs to be analyzed. Will this even move to begin with? And I can't answer it because they didn't give me enough information. And I kind of overlooked that, saying, well, since he didn't give us, and the question says, what is the speed when it gets back? He's implied in all there that it does actually move. But, I mean, if I get my calculator out here, 100th, I mean, this is 25 newtons, right? The force that way. This is mu s times a 19.6, right? And if those were equal, you know, question mark, they could be if this coefficient is as big as 25 divided by 19.6. Now, it's highly unlikely that it is, which again, I think is all the more reason why the author gave these numbers. So it's very likely that this thing will start to slide to begin with. Okay. There's another question here, and maybe I'll just touch on it because it's in the next problem, is will it go all the way back to equilibrium? Because right now, let's just say the coefficient of static friction was less than this, so it would actually start to move. Now, once it starts to move, we no longer have static friction, we now have kinetic friction. Fair enough? Now, our number for kinetic friction is not that great, so this thing probably moves back close, but wouldn't there be some point before it got to equilibrium where the force from the spring, because remember the force from the spring is getting less and less and less and less, because the force from the spring has to do with Hooke's law. So there could be a point here where before we get back to equilibrium, the kinetic friction is more than the force from the spring. I mean, there'll be some point where they're equal first. Then further on, this is more, and then the block is slowing down. And it may actually slow down and stop it before it can get to equilibrium. Now, I doubt in this case, based upon these numbers, but this would be actually slowing down before it gets to equilibrium. Which is why I picked the next problem. So maybe I should move into the next problem. That's a little added subtlety there. Yeah.
Were there any problems where it's a oscillate after?
Oh yeah, and then of course this problem only said, go to equilibrium, and that's it. But I think you begin to see, now wait a minute, what about after that? After that it would now compress the spring, which would then send it back. And this thing would oscillate back and forth, right? And without any friction it would keep doing it forever. With some friction it would go slower, 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 and eventually stop. And as we just talked about, it may not even be at equilibrium, it may be off a little bit. So much harder question. Much harder, which is why we'll do it in chapter 15. Okay? So it's a good question, but and that one might not be too hard to tackle, but we're going to wait until chapter 15 for that one. So, as we get into, and that's the name of the chapter, oscillations. And it looks at all kinds of oscillations, not just this one. And that's why the author waits, because he wants to also look at rotating oscillations. You take a disc and wind it up on a rope, and you let it go. It will unwind and then wind up, and then unwind, and it will oscillate too. So in chapter 15 we'll do a lot of oscillations. Starting with this one, this will be the easiest oscillation. So more to come. All right, so that was that 14? Yeah. 14. So the one I was referring to then is in 23. 23 is very similar to this in some senses, but also has a nice little added different pieces to it that illustrate this point well, that aren't I really doing the same thing again and again and again and again? I'm applying conservation of energy, but each problem is a little bit different. Each problem has different energies. Some go uphill, some don't go uphill, some have springs, some do have springs, some have friction, some don't have friction, and we need to look at each individual case here, and so that's why, you know, back to the top of your syllabus there, physics is about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. Just what is that fundamental idea, and now just apply it to that case, which I know is not so easy, but that's, you know, 2 hours later you'll be done with your first problem, you know, but hopefully not the test, because there's 5 problems and you only have 2 hours. So, but as you're doing the homework, that's kind of where you start with. So look at 23 here. 23 says you have a toy cannon. It uses a spring to project a 5.3 gram rubber ball. The spring is initially compressed 5 centimeters and has a force constant of 8 newtons per meters. When the cannon is fired, the ball then moves 15 centimeters through a horizontal barrel. The barrel also exhibits a constant frictional force of 0.032 newtons as it moves through the barrel. With what speed does the projectile leave the barrel of the cannon? B, at what point does the ball have its maximum speed? C, what is this maximum speed? All right? So maybe draw a picture again here. Here we have this cannon, and they did say it was horizontal. So in my mind, it kind of looks like one of these World War or Civil War cannons here. What do those things look like? Something like this here? Okay, so, but it's nice and level, okay? Which probably a real cannon, I wouldn't think, should be level. I don't know, but you know, you're firing it level so that you can, you know, do the problem easier, really, I guess. Although maybe I should tell you, I fired my little air cannon level last night. I think did I tell you guys my? My son has this introduction to engineering class at his high school, and they've been building different projects, and the latest one was a tennis ball launcher. It was really cool. Although I think he got bored and I got carried away here, but yeah, and you know, they had different designs going, and they had to give it to the teacher, and you know, we started with just kind of, you know, like a crossbow type thing. Anyways, so we eventually ended up making this air cannon, and so we 3 feet PVC pipe by 3 VC pipe, really cool, and then a long PVC pipe at a 45 degree, and the tennis ball drops down there, and so we fill it up with the compressor and you turn it. And we're curious how far it was go. So a couple weekends back, and so I was telling some of you, we dropped a tennis ball in there, 300 feet. I mean, it went the whole football field. You know, we were down in the stadium. I was like, okay, this is good. And so he said, I want it to go the whole football field. Okay, so we were firing from one end zone and went out of the other end zone and landed in the high jump pit. So I'm like, all right. So anyway, so he took it into class and they did that. And anyway, so the cousins were over last night. So we had some chicken and some visitors and da-da-da. And they see it sitting out there, you know. It's like, oh, can you fire that? And I said, we can't fire it here. It'll, you know, I don't know where to land. It's going to do some damage. So after a little bit of thinking, we go, you know what we could do, though? We could fire it level. And so I had them hold it up, and we just blasted this thing. It was nice. I fired it into the block wall, and the tennis ball just ripped in half. Just, whoa, I've never seen that before. Anyways, I told you it fired fast, so we fired it a few times level. So that was our fun last night. Then so did the soda cans was cool too. We tried that because the soda cans come ripping out just about as fast as a tennis ball, but they tumble, so they don't go out of the yard. So they go. Phew. Although it got windy after a while, so they were going like this. Then one got a little too much wind and ended up in the neighbor's yard. So I'll have to go apologize tomorrow or something. You know, I had the cousins over last night, and there's, I think, a can in your backyard. but no damage. And maybe I shouldn't tell you this. I'm certainly not going to tell my son, but so I was flipping on YouTube, and these guys put frozen sodas in theirs. And they shot it through a block wall. And I wasn't going there, so I was like, whoa, 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 whoa. Somebody's going to get killed with this thing if you're not careful here. Tennis ball was enough here. All right, anyway, so that's the idea. So we got this level cannon, and here's our level cannon. But if we go back and read these numbers, they're real careful to say that there's a spring inside, okay, something like this. Yeah, so it's not a real cannon. There's not gunpowder in here. It's a toy cannon, all right? And you put the ball in here, but I hope you read in the problem here, if you haven't had a chance to play with a toy cannon, the spring is not the whole length of the barrel. That's key to this problem here. Watch, we'll read it again here. A toy cannon uses a spring to project a 5.3 gram rubber ball. The spring is initially compressed 5 centimeters and has a force. When the cannon is fired, the ball moves 15 centimeters through the horizontal barrel of the cannon. Okay? So what they're saying here, and maybe I'll change colors so you can see it, but the ball gets lodged back to here as we compress it. And so this is the 5 centimeters. But the barrel is longer than the spring is compressed. Fair enough? And so keeping that in mind, we'll avoid any problems, hopefully. But that's an important part to see in that physical picture. Here's where like I said, the physics comes into play, the reading of the problem, understanding of the problem. Otherwise, you're going to be tempted to put a 15 or a 5 in the wrong place here. We need to understand where to put it. And it's, like I said, actually the main reason I picked this one was for that issue coming up in B. But here in Part A, we need this. This is a nice, secondary learning lesson here of this cannon. And so there's our had an epiphany too. Can't figure out where to put this cannon. It's too big, and I got too much junk in my garage. So maybe it should be here. Yeah. What if we could hit the stadium from here? Oh, yeah. So still got to keep it at home for a while. It's a good conversation piece.
I'll bring the photos.
Yeah. Well, yeah. So one of my cousins did have an idea. They did say, what if we went to the beach and shot it out to sea? And then who cares how far it goes, right? So they were wanting to try all kinds. I thought that was good. They were suggesting a hard ball, avocado, potato. Of course, then my brother-in-law said, yeah, and then there's going to be dead whales washing up with baseballs in their blowholes, So hopefully that wouldn't happen either, too. So, all right. So in this problem here, the first part of this is, I think, what is the speed? Let me read A here. What is the speed of the projectile as it leaves the barrel of the cannon? So the question is, what's the speed right there? At least that's the first question. So again, this is that part of get a well-defined definition here to your initial, your final, understanding the problem. And then once you put it into your equation, it goes really simple here. But it's a good physical picture and a good strong definition of beginning and ending here. And I'll start off then. Okay, so my initial energy is equal to my final energy. So what is my initial energy? Well, where's my initial position? And I would say the loaded position. That's what I want to call the initial position. So don't have to worry about the external force from your hand. And I should do one of those. I'll do that one next here. But I'd say, look, it's loaded back into here. And so then I can say, well, how much kinetic energy does it have? 0. How much gravitational potential energy does it have? Okay, again, we can pick y anywhere we want. Where do you want to pick y? How about the height of that horizontal barrel, so that the height is always 0? Okay, so we don't have any kinetic energy to start with. We don't have any gravitational potential energy to start with. It's kind of like the problem we did, before, where we said, look, we don't have to worry about that. But it does have the spring. So the spring is a 1/2 kx initial squared. That is the original or beginning kinetic energy here. And they've even thrown us a little twist here, I think, with our units, because they have said that the force constant, the K, is 8 newtons per meter. But they compressed it how far? 5 centimeters. So again, let me put it in meters. And if you want to call that negative, you're more than welcome. Since you squared it, doesn't really matter. So compressing a spring or stretching a spring takes the same amount of energy there. But to be consistent, I'll call that direction, the left, negative, and then we'll go to the right as positive. But that's how much energy we start with. And then where does it go as it travels through the barrel? Well, it goes down the barrel to here. When it gets to here, that's the problem. What is the speed? So there would be the factor, the kinetic energy, which would lead me to its speed, which also has another little twist in the units. You got to be careful because they gave me 5.3 grams. I don't want grams. Why? It's in joules. I want kilograms here. So as I go to this next line, it's 0.0053 kilograms times v squared. So watch the units there as they give you your units in grams. What other energies does this thing have at the end besides kinetic? The heat energy, right?
Did it give us a...
And they did. I'll go back and read it here. But they said here that as the ball travels through the barrel, it has a constant frictional force of 0.023. So they didn't give me a coefficient. They actually gave me something better. They just gave me the friction right out. All right. So how am I going to calculate this force of friction? I'll call it kinetic times distance traveled. So the force of friction is the 0.32 newtons. Distance traveled?
15 centimeters.
15 or 5?
Well, would it be from the hole?
Or is it 10? No. Or, no. Yeah, no. It's not the 10, it's not the 5, it is the 15, yeah. Oh, and then of course, converted into meters. Yes, definitely. Yeah, yeah. Okay. So, again, it's the main reason I picked this one for A. Actually, B is really the more reason, but like I said. But, again, that's where you got to be careful. And for those of you who see it, you're thinking it's not a big deal. I would have never even asked the question 10 or 5, right? Unless you don't see it, right? And that's where the physics comes in. Don't get yourself confused on these numbers. It's clearly the 15 because there's friction, 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 the whole thing. And so it's the 5 here because that's where the spring is pushing. It is 15 here because that's where the friction is pushing. And then once you know that, it's like, well, yeah, what else would I have done? Sure. Okay? And then, of course, you can see that there is only one unknown, and so now it's calculator work at this point, and you can then solve this. So on this side of the equation, it's 1/2 times an 8 times a 0.05 squared for the total energy we start with. Subtract off how much we end up losing because of the heat. Okay, then I guess I'll multiply by the 2 from this one, divide by the 0.0053, and now take the square root of all of that, and I get a 1.4. Hopefully you guys get the same, and then carrying my units through, it's 1.4 meters. Oh, and then we can say plus or minus because it's a square root, but now let's make a decision. It's never two answers. It's what does it come out to be? And this one is going to the right, so it is the positive one. So this is a positive 1.4 for the velocity when it comes out of the barrel.
When we talk about speed, are we always talking positive, no matter versus just pure velocity?
Probably. It certainly, and that certainly could be the case that he's arguing. What does he say here? What's the speed? And by applying speed, he means the magnitude. And magnitude is always a positive number. That's more semantics than it is physics, and I'm not worried too much about that on a test, so you wouldn't lose any points to it. But I also don't want to underestimate semantics, because in the real world you got to communicate with people, and they got to know what you're asking or what your answer is, and that kind of thing. So, but yeah, I think because he says speed, and speed implies magnitude, and magnitude implies positive, that we should be putting a positive number no matter which way we set it up, because it's only going to the right because we drew it to the right. Right? I mean, we could have easily drawn this cannon facing the other direction. And we would be, it would be in my case, while I'm grading the test, here's probably what I would look for. I would look, if they called this negative right here, that would tell me, okay, they've chose a direction, so they're going to call this positive, And so chances are they're going to put that one a positive. If they start putting that one negative and that one negative, that's like, really? I mean, that's not even consistent with itself, nor is it consistent with the fact that speed should be a positive number. So it's not consistent either way. So I have more of a problem with that than if they're both all positives. Yeah. So then B here is, like I said, a real neat one. Going to make you think here. It says, at what point does the ball have its maximum speed? So is its maximum speed when it leaves the barrel? No. Is the maximum speed when you start to fire it? No. Is the maximum speed right here where the spring gets to its full extension? No. And that's why I picked this. It's so easy to say that. Let's look closely at this free body diagram. Free body diagram. So here's this rubber cannonball. And it's being pushed this way by the force of the spring, which is equal to a minus kx. Fair enough? Or at just absolute value, it's just kx. Right? Not worrying about pluses or minus for a second.
So
Yeah.
what are we looking for in this part as well?
Where does the ball have its maximum speed? Okay? Anything pushing back on it? Yeah, that's that friction right there. 0.032 newtons. Now, let's start at the very beginning. At the very beginning, that spring is pushed back 5 centimeters. So if I were to calculate the force from the spring, which is 8 newtons per meter, times 0.05 meters, 40 with 2 decimal places, is that right? That would be the initial push from the spring. Fair enough? And I would say that that number is quite a bit more than that number. So at the beginning here, as most of you already were thinking, the spring would be much more than the frictional force. And this thing would start going. Push, 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 push. Fair enough? But what is the force from the spring when you get all the way back to equilibrium? Doesn't the force from the spring go less and less and less? And by the time you get back to equilibrium, doesn't it go to 0? So wasn't there a point before it got back to equilibrium where the force from the spring and the force of friction were equal? That's the point where you get your maximum speed. Anything over here beyond that point would be a force from the spring that is greater, and it would be accelerating, 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 accelerating. But as you get close to equilibrium, the force from the spring is actually going to be a little bit lower. And what will happen now is it will begin to slow down, even though you haven't got to equilibrium yet. This thing starts to slow down before it gets to equilibrium. And that's what you had asked there about the force of friction and then the force of kinetic. The fastest point is not back here. It is a little bit before, maybe there. And again, this is the one that's absolutely important. You see that physical picture here. I mean, we're going to write an equation. It's going to be an easy equation to solve. But you get all of this from the physical picture. What is going on in that physical picture? You got to lay out this equation. And if you don't lay it out right, or you don't get that in your mind correctly, you're going to just say it had its maximum speed here. And if you did that, you would probably write out this exact equation with changing the 15 to a 5, and you would get the wrong answer. It is not where it has its maximum speed. So how do I solve B? Well, I guess I would solve it for when does the force from the spring equal the 0.032 newtons, right? I know that initially it's greater than that. And then it gets less and less and less. So solve this for x. And I'll just, worry about absolute value here. So the absolute value of x would then be 0.032 newtons divided by the k, which is 8 newtons per meter. And so 8 goes into 32, must be 4 times. 4. And then 2 zeros, newtons cancel with newtons, and you're left with a meter. Or if you like, 4 millimeters. So it is close to equilibrium. Closer than I guessed. I was thinking it would be a whole centimeter or something, but it's pretty close to equilibrium before we get a balanced force. And from those last 4 millimeters then, right here, we're actually slowing down a little bit. Yeah?
The force of the spring and the force of kinetic friction were equal. Wouldn't that say it's not moving in the x direction?
Not accelerating. Still moving,
Yeah.
but not accelerating. Yeah. Yeah. All right, now that is just the beginning part. Now we can go back and use conservation of energy and find its speed. So let's actually answer that question. What? Oh no, I'm sorry. B is just where. So I guess we found the where. And so the where is, and maybe I'll put it, I think I kind of marked it here in red, but I should maybe mark it in blue so it kind of stands out. But it's right there, roughly. 4 millimeters before we get back, to equilibrium. At that point, the force from the spring is the same as the friction. And then beyond that, friction is a little bit more, so it's already has started to slow down. And of course, we'll go slower, 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 slower until it gets to the end of the barrel. So this speed here is much slower than its fastest speed. And so I expect to get a speed greater than my 1.4 here. And so now I can go on to C, which says now that you found the place that it has its maximum speed, then what is the value of that maximum speed? And so we can put our 1/2 kx initial squared equaling 1/2 mv final squared plus 1/2 kx final squared plus the force of friction times the distance traveled. And notice I put an equation here for the energy of the spring because we are not back to equilibrium. Although we're not far, so this number is kind of small. But as we put this number in, this is the 1/2 times the 8 times the 0.05 squared. This is the 1/2 times the 0.0053 final speed squared. This is the 1/2 times the k, which is the 8, and then here 0.004 squared. That's where this comes into play, right there. There is still some energy in that spring. Now, very little, which is the whole reason it doesn't make it go faster. It's not much there. And then we've got the force of friction, 0.032. And then how much distance did it travel? 0.05 minus 0.004, right? Because it didn't quite travel the whole 5 centimeters. It's shy of that. And so, only unknown is V final. Okay? And so now we got a lot of calculator work still, but hopefully you see where each individual number comes from.
So we were finding from the rest, so that speed of the whole distance, taking away that little
Yep.
4 millimeters.
So we're trying to find the speed right here, 4 millimeters before it gets back to equilibrium. Because B, that's where we have discovered where it is at maximum speed. So let me call that the final position. So my final position is 4 millimeters before I get back. Because I want to find the speed at that point. So the speed at that point, I need to put a 4 millimeter there, and I need to put distance traveled, which would be the 5 minus the 0.004. And then I should get my speed when I get back to that location here. So one side of the equation, it's 1/2 times 8 times 0.05 squared. And then I will subtract off this term, so minus 1/2 times 8 times 0.004 squared minus 0.032 times 0.05 minus 0.004. So I'll subtract those two off. Then I'll be left with that one, so it'll be times 2 and divided by 0.0053. Square root of all of that is about a 1.79. So there's the speed of the maximum speed of this cannon. Yeah.
Will the spring ever push past the equilibrium point?
In our simple models, no, because I think what you were getting at is like back in here, if the spring had gone past equilibrium, then you would say, well, some of the energy's in the spring, right? And this would actually be a slower speed. And I would say yes in the real world. But if you'll notice, our springs have no mass. So for them to go forward and then stop instantly takes no force. There's no mass. So you can have infinite acceleration with zero mass and zero force. So yeah, it's a little disconcerting and a little bit fictitious. But until we get to higher levels, we won't put any mass with our springs. So we'll just say right now they're massless. And I got to admit, that can often be troublesome because I have had students who bright students who struggle with this problem, who look at it and say, some of the energy has to be in that spring, and they're really concerned about that. And they know they're not doing it completely right when they do this. But then they don't know how to do it completely right because we haven't even addressed that yet. So I want to emphasize that. Our springs are massless springs. They're not real springs. Like a lot of our surfaces are frictionless surfaces. They're not real. But we started adding friction, obviously, in chapter 5 and 6. So each chapter we get closer and closer to the real thing,
Is that the same with our pulleys?
And our pulleys too. Notice our pulleys have no friction and no mass. And because of that, we don't worry about the energy associated with them. But again, that will change. I think we changed that in chapter 11. Adding mass to our springs we never do till next semester. So we never do this semester. We do later on. Adding mass to our pulleys we will this semester, just not yet. So we keep adding things. Getting more and more realistic, if you will. Well, I haven't done one where you have an external force, so let me jump on 15. 15 has one, and so finally one where we got that other term, and I think we've done all the other terms. I can only wish that there would be time to do even more, but at least this one means I've done all the terms now. I've done the kinetic energies, the potential energies, the kinetic energies. I've done the heat of the friction, and now we can do an external force here. And 15 is just that. 15 says a crate of mass 10 kilograms is pulled up a rough incline with an initial speed of 1.5 meters per second. The pulling force is 100 newtons and it is parallel to the incline, which makes an angle of 20 degrees with the horizontal. The coefficient of kinetic friction is 0.4 and the crate is pulled up 5 meters. How much work is done by the gravitational force? B, determine the increase in internal energy due to the friction. C, how much work is done by the 100 newtons. D, what is the change in kinetic energy? And then finally E, what is the speed of the crate when you pull it the full 5 meters? Now, I'm just going to put all those together, A, B, C, D, and E, because those individual questions are each individual term in the conservation of energy. What is the energy of this one? What is the energy of that one? So I'll solve them separately also, but let's just write out the whole thing. I mean, let's just say the question says, what is the speed of the crate after you pull it for 5 meters? Is it going faster? Is it going slower? Part of me wants to say it's going faster because somebody's pulling this pretty hard, 100 newtons. But the other part of me wants to say it's going slower for 2 reasons. A, it's going uphill. B, there's friction with it. Only the numbers are going to tell me which one is bigger. Does it end up going faster or not? There is positive work and there is negative work. So I don't know, but let's work it out here. So again, pause for a little bit and give yourself a good mental picture of what's going on. They said you had a crate. They gave its mass, I forget what it was here, a crate of mass 10 kilograms. So here's the 10 kilogram crate. It is pulled up a rough incline. Okay, so that keyword rough means we're going to have some kinetic friction as we are sliding up here. Okay. It has an initial speed of 1.5. So right here, it has a 1.5 meters per second initial speed. Rough surface. I don't know if this helps. It always helps me. Kind of squiggle, 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 squiggle. Okay. A pulling force of 100 newtons is applied parallel to the incline. The incline makes an angle of 20 degrees with the horizontal. All right, so I already put the 20 degrees on here, but they are saying then this is your pulling force, F. And it's pulling parallel to the incline. So they're not saying it's, horizontal force. And actually being parallel to the incline is a little nicer in terms of calculating work because we have, remember, the force times the distance moved times the angle between them. And in this case, well, I'll talk about that one soon too. But that's important. We got the direction here. Okay? What number was this? 15? All right, so we pulling it at 20 degrees. The coefficient of kinetic friction is 0.4, and we pull it up 5 meters. So coefficient of kinetic friction is 0.4. We are going to move from, say, here up to here, and we are going to go 5 meters. All right. And so I'll pause again, right? Got a good physical picture of what's going up? This crate up the hill? And like I said, part of me goes, hey, this is going to go faster because somebody's pulling it. Yeah. Part of me's going, wait a minute, they're pulling it uphill. And they're pulling it with friction. So I'm not sure if the friction in uphill is more than what the person's pulling. If they do, this crate's going to slow down. So it's not going to be at 1.5. It's going to be a little slower. But on the other hand, if my pull is more than the friction and the gravity combined, then it's going to be going a little bit faster. So let's find out. And that's why they ask you to do those individual pieces. They say here, all right, let's take the initial energy and says it equals to the final energy. And again, writing these out, this would be initial kinetic, initial gravitational potential, initial spring potential, plus this outside one. That is the whole reason I picked this one. It's the first time we've done, let's worry about the energies from the outside. That has to equal to what? Well, it's got to equal to the final kinetic and the final gravitational potential and the final spring and the heat that's created along in the process.
No spring.
Oh, good. So there's no spring. So just for completeness, I put everything. But hopefully one of the things you notice right away, there's no springs to worry about. So I'm going to just throw that one out from the get-go. But I think the other ones are all here, right? There's kinetic energies involved. There is gravitational potential energies involved. There's an outside force involved. And there is a heat involved here. So let's start here with this one. Kinetic energy. Wouldn't this be 1/2 times m times speed squared? Okay. And of course, maybe that's part of the problem is what do you call initial? I mean, be real clear in your mind. And since the energy is always equal, initial could be anywhere you want it to be, and final can be anywhere you want it to be, because initial equals final always. Could be here and here, could be here and here, here and here, you know, anywhere you want. Okay? And so, of course, in my case, since I am given this information, it makes sense to call this initial. They're asking for what is it over here, so this is going to be my final after I pull it up 5 meters. So this is my initial speed, 1.5. How much gravitational potential energy do I have? Yeah, that begs the question, where do you call y equals to 0? So we got that choice. So make it clear where you want to call y equals to 0. How about right here where it starts? All right. And of course we can measure from the top edge or the back edge or the center, wherever you want. But since I kind of measured the incline from the front edge, why don't I go ahead and measure the height from the front edge? And as many of you said, why don't we call that y equal to 0? And I like it too, and I agree. So I'm going to say the initial gravitational potential energy is 0 because that's where I called y equal to 0. No, notice I don't even care about how far this incline goes back down, right? It's not needed. Notice I don't care if it's on a table off the ground. It's not needed. So that's why, again, you always have that freedom of choice to pick your y equal to 0. And well chosen, it'll save you with a lot of work. So, all right. Good luck. I bet there's a lot of others of you in here too, right? Who else got an interview today, no? Oh, Lily does. Good luck. Didn't want to leave anybody out. Okay. And so this is this added piece. And like I said, this is why I picked this one, because I haven't done this one yet here. All right. What is the work from this outside influence? And that's the one that I purposely left alone at the beginning of this because it can be so different. We just have to look at every case by itself. And so let's look at this one by itself. Let's look at this work that is done by this outside influence. Remembering that this is our definition of work, right? And so we go all the way back to the beginning of chapter 7 and say, how do you calculate the work, done by this object here? This is the energy you are adding into it. All right. Well, I guess the dot product means, and with any dot product, there's 2 ways we can look at it. We can look at it as the magnitude of the 2 multiplied together times the cosine of the angle between them. Or we can look at their x and y components. And I think I mentioned that I like this. This is very physical. I like the polar coordinates more than the rectangular coordinates. The rectangular coordinates is usually what the beginning student feels a lot comfortable with because it's x's and y's. But here it's more physical. And in this case, it's a very easy one because what is the magnitude of the force? 100. And what is the angle between the force and the direction it moves? 0. And that's, I hope you see, it's 0 degrees. I want to pause there. It's not 20 degrees. What's 20 degrees? The slope of the incline. Okay? But it's easy to mix that with what direction does it move? Well, it moves up the incline, right? What direction is the force? Up the incline. The movement and the force are each up the incline. And so this angle is the angle between the force and the direction it moves. That's where that came from here. So don't fall into the picture. Oh, there's a 20 degrees in here. So what? That's not what that angle is after. That angle is after the angle between them. And of course, what makes it an easy calculation is what is the cosine of 0 degrees? 1. And so this reduces down to 100 times the integral of dr. And what's the integral of dr? It's just the distance you travel, which is 5 meters. So this is 100 newtons times a distance of 5 meters for a total of 500 joules. And so this outside piece is adding 500 joules of energy. Okay? Yeah.
Can you explain the zero again? I didn't quite get it.
All right. 0. The angle in this equation is the angle between these two vectors. Those two vectors are what is the direction of the force and what is the direction it moves.
Oh, okay. So they're the same direction.
And they're the same direction. So now they're 20 degrees from the horizontal, but they're same direction. There's no angle between them. Yeah.
Just to verify, would that be, would the units for velocity be second rather than?
Oh, my bad. Yep. That's, I have a tendency of doing that a lot. I guess I just write slow. You know, I'm still writing the S and I'm thinking I got to square it, and I put a 2 down there. Just gonna have to write faster, or maybe I should think the positive. I just think too fast. Yeah, that's it. I can think, but it's easy to think faster than you talk or you write, and so yeah. So, which then really can foul students up because you write funny things and you say funny things, and in your mind it's all fine, and students are confused, and so
We're just listening to you.
gives us good stories to tell our other classes, you know. You know what the student asked? He asked how long the meter stick was. That was so I have had that question, by the way. So I think I've shared that with some of you. Yeah. So how long was the meter stick? It was a final exam too. Did I tell you guys this? Yeah. The students came up and said, I think I nailed that final exam. I did really good. I know I'm going to get that A. It was just I had a little trouble on that last one. That last one, as it swung down, I left it in terms of L because I didn't know how long the meter stick was. Really? So, and then, you know, maybe bad part of I didn't even address it. Just all right. See you next semester. Have a good break. Yeah. I'm sure he figured it out within minutes walking out the door. You know. So, yeah. All right. So, anyways, this was a big reason for this one. So this is how much energy we're adding to it. And if that energy we're adding is more than be taken away by the gravity and the heat, then this is going to end up going faster. If not, it's going to end up going slower. And I still don't know, but let me keep going with it. So on the other side of the equation, this would be a 1/2 times 10 times the final speed squared. Okay? And so that's what I'd like to know. What is that number? And I'd be curious to know if it's more than 1.5. Oh, let's look at this one then. What's my final gravitational potential energy? So 10, 9.8, and what's y? Ah, good. So it is, I hear sine 20. And then, of course, the 5 is maybe, hopefully, the obvious one I didn't hear. But it's not just 5, right? It's 5 sine 20, right? Because it moves 5 up the incline, and you got to take a component of that. So there it is, 5 sine 20. So magnitude component. How far up did it go? Okay. And so that's that term. And now this one, the heat. So here's another fun one to do. How much, I'm going to do it quickly here. I guess we'll be done here. Heat. Well, that is, of course, the force of friction times the distance traveled. Now maybe I'll start with distance traveled. How far did it travel? 5? 5 sine 20? 5 cosine 20? It's just 5. right? It is 5. That's how far it traveled. It traveled up the incline 5. Vertically, it went up sine 20. Horizontally, it went cosine. But that's not what I care for that one. That one, I care about how far did it actually travel. So it actually traveled 5. Now, maybe the harder one here is then what's the frictional force? Yeah, they gave me the coefficient, but I get the normal force here. So this is the coefficient of friction times the normal force. Now the coefficient of friction is 0.4, so that one is given. That depends on the surface and what it's made out of and how well it's polished and all that good stuff. But it's the normal force. It's going to take me back to chapter 5 and draw a free body diagram. So maybe I'll do that over here and say, okay, what is the normal force? And I'll ask, does the normal force always equal mg? No, and I don't think it does in this case. So let's draw the block by itself. What forces are on this block? Well, gravity, mg. Force of friction, normal. Any others? Yeah, that tension or rope, whatever the 100, they didn't really say if it comes from a rope, so I'm a little hesitant to call it tension. But whatever it is, there's 100 newtons pulling on it. And I think that might be it. Let's see, we've got the table touching it. That's those two. We've got some other object pulling on it, and then gravity. Yeah, so that's it. And so if I take an axis that is tilted, and I look at the sum of the forces in the y direction, I've got normal force pushing up. This does not have a normal force. But pulling into the incline is not a full mg. It's mg times the cosine of that angle. And is that 20 degrees too? Okay, good. And since we're short on time, you guys sound like you remember it from chapter 5. But that is also the 20 degrees. So knowing that, I can then write this as 10 newton or 10 kilograms times 9.8 times cosine of 20 degrees. So putting all that together for your heat then is coefficient of friction times mg times cosine of 20 degrees, so there's the force of friction, times a distance of 5 meters. And then, maybe we're out of time, but hopefully you see that in each of these questions that they ask. As I come here, look at A. How much work is done by gravity? Well, that would be that term, right? There's the gravitational term. B. Determine the increase of internal energy. That's the heat. So that's that last term. C. How much of work is done by the 100 Newton force? That was that term. That's the 500. D. What is the change in kinetic energy? Well, you can see now, if we know that one, and that one, then the three of those would be the change in kinetic energy. And then finally, I'm out of time to solve it for you, but the only unknown here is what is the speed. And so I'll let you go, but I got to just know, does this block go faster or slower? It's been bothering me for 10 minutes here. So we'll find out here if it does it end up going faster? All right, so we'll see if I get faster here too. 0.1 times